September 3, 1944, Ebbw Junction, South Wales. A captain from the U.S. Army Transportation Corps walks along a siding where over 300 steam locomotives sit waiting. Not British engines, not captured German rolling stock, American-built machines, fresh from transatlantic crossings, preserved in thick coats of cosmoline grease and wrapped in protective sheeting. He stops beside locomotive number 1847, recently arrived from Baldwin Locomotive Works in Philadelphia. The protective covering has been partially removed for inspection, revealing a machine that defies every principle of locomotive design he learned before the war. This is crude, he thinks, examining the welded seams and simplified fittings. No ornamental brass, no polished domes, cast steel where there should be forged components. This looks like something built to be thrown away. But the specifications tell a different story. The engine measures 62 feet 9 inches long, weight approximately 160,000 pounds without tender, 8 driving wheels, each 57 inches in diameter, 2 cylinders, 19 inches bore by 26 inches stroke, boiler pressure 225 pounds per square inch superheated, tractive effort 31,490 pounds of force, capable of hauling freight trains weighing 1,000 tons or more across war-torn European rail networks. Yet everything about the design prioritizes speed of manufacture over longevity. The locomotive bed is cast steel, faster to produce than traditional forged frames, but less durable. The boiler uses welded construction instead of rivets. The running gear features simplified bearing arrangements. The cab is Spartan, barely enough shelter for the crew. No decorative elements, no refined touches, just functional machinery built to specifications measured in weeks, not years. He pulls out his inspection notes. Between 1942 and the present date, American manufacturers have produced over 2,000 of these engines. Baldwin Locomotive Works, American Locomotive Company, Lima Locomotive Works, all building to identical plans, using interchangeable parts, targeting production rates of 15 to 20 locomotives per month per facility. The numbers are staggering for machines this complex. The broader context makes the crude design suddenly comprehensible. 500 miles to the southeast, Allied armies are racing across France toward Germany. General George Patton's Third Army has covered 600 miles in 3 weeks. The First Army is approaching Belgium. The advance is so rapid that supply lines, stretched from Normandy beaches to frontline positions, are approaching collapse. The Red Ball Express, that heroic truck convoy system, is delivering 12,000 tons of supplies daily, but it's not enough. It's never enough. The French railway system, methodically bombed into ruins before D-Day to prevent German reinforcements, remains largely unusable. Bridges destroyed, marshalling yards cratered. Most critically, virtually no functioning locomotives. The Germans hauled away or sabotaged their remaining rolling stock during the retreat. The Allies control thousands of miles of track, but almost nothing to run on it. The liberation of Europe was at risk of stalling completely. If you want to see how they solved this impossible situation, please hit that like button. It truly helps us continue sharing these stories. Subscribe if you haven't already. Now back to the solution. These crude American engines sitting at Ebbw Junction represent the solution. Not elegant, not refined, but capable of being mass-produced, shipped across an ocean, and put into service within weeks. Each locomotive can haul what would require hundreds of trucks to transport. Each engine burns coal, abundant in Europe, rather than precious gasoline needed for tanks and trucks. The concept is revolutionary. Disposable industrial machinery built for immediate wartime use, designed to be discarded when peace returns. It violates every peacetime principle of locomotive engineering. It might also win the war. The story of how this happened began 3 years earlier when American military planners recognized that the coming European campaign would be won or lost on rails. 1941, Washington, D.C. The United States Army Transportation Corps faced a fundamental problem: how to supply a modern mechanized army operating thousands of miles from American ports, fighting across a continent whose infrastructure would be systematically destroyed before invasion. The mathematics were sobering. Historical analysis of the Wehrmacht's campaigns demonstrated that mechanized divisions consumed approximately 750 tons of supplies daily during active operations: fuel, ammunition, food, replacement equipment, medical supplies, spare parts. An army of 28 divisions would require over 20,000 tons delivered to forward positions every single day, continuously, regardless of weather, enemy action, or infrastructure damage. Traditional supply methods couldn't scale. Port facilities could unload cargo, but moving that tonnage from ports to frontline positions required transportation infrastructure. Trucks were mobile but consumed fuel themselves, precious gasoline burned simply to deliver more gasoline. The Red Ball Express, created in 1944, would ultimately demonstrate both the heroism and the limitations of truck-based logistics. At peak operation, 6,000 trucks driving continuous loops delivered 12,000 to 13,000 tons daily, while consuming fuel, wearing out tires, breaking down, and requiring thousands of drivers and mechanics. Railways offered dramatically different economics. A single locomotive pulling a 50-car freight train could transport 1,500 to 2,000 tons in one trip, equivalent to hundreds of truckloads. Trains consumed coal, not gasoline. They required fewer personnel per ton delivered. They could operate day and night regardless of weather. Rail transportation was 5 to 10 times more efficient than trucks for bulk cargo movement. The challenge was that European railways wouldn't survive the invasion. Allied bombing campaigns intentionally targeted rail infrastructure to prevent German reinforcements from reaching invasion beaches. Bridges would be destroyed, marshalling yards would be cratered, rolling stock would be damaged or removed. The successful invasion would leave the Allies in control of thousands of miles of track but little functional equipment to operate it. Military planners considered several approaches. Repair captured German locomotives? Impossible. Hundreds of different designs, non-standardized parts, complex maintenance requirements, likely sabotage. Use British locomotives? British railways operated on different loading gauges, track spacing and clearance dimensions incompatible with continental European standards. Build locomotives in Europe? No functional factories in liberated territories, and months required to restart production. The solution emerged from a different direction. Design a standardized locomotive specifically for military use, manufacture thousands in American factories, ship them across the Atlantic, and establish them as the backbone of liberated European rail operations. The design specifications reflected military requirements rather than commercial railway standards. Loading gauge must fit British and continental European railway restrictions, smaller than standard American locomotives. Production speed, components designed for rapid manufacture using mass production techniques. Simplicity, minimal complexity to reduce maintenance requirements and training time. Standardization, complete interchangeability of parts between all units. Durability, sufficient for wartime operations but not optimized for peacetime longevity. Fuel, coal burning to use locally available fuel rather than imported petroleum. The design contract went to Major J.W. Marsh from the railway branch of the Corps of Engineers in May 1942. Marsh led a committee including engineers from Baldwin, Lima, and ALCO, the three major American locomotive manufacturers. They adapted a Baldwin 280 design from World War I, updated in the 1930s, incorporating austerity principles pioneered by British wartime locomotive construction. The resulting design, eventually designated the S160 Class, was deliberately crude by peacetime standards. Cast steel frames instead of forged components, welded boilers instead of riveted construction, simplified bearing arrangements, minimal finishing work. Every design choice prioritized manufacturing speed over traditional quality standards. Production contracts were distributed among all three manufacturers to maximize output and ensure supply continuity if any facility experienced problems. Baldwin Locomotive Works in Eddystone, Pennsylvania. American Locomotive Company in Schenectady, New York. Lima Locomotive Works in Lima, Ohio. Each manufacturer received identical specifications and committed to interchangeable parts. Any component from any factory would fit any locomotive. First deliveries began in late 1942. The locomotives were shipped partially disassembled to fit in cargo ship holds, accompanied by assembly teams and spare parts. Initial deployment went to Britain, where they operated on British railways during the build-up to invasion. This served dual purposes: testing the design under operational conditions and increasing British rail capacity to handle military cargo movement. British crews gave the S160s the nickname Rattlesnake due to the distinctive clattering of their simplified rod bearings, a consequence of the austerity design that sacrificed refinement for manufacturability. American crews called them various things, often less flattering: spam cans on wheels, GI engines. The locomotives were workhorses, not thoroughbreds. By mid-1943, production had ramped to full capacity: 15 to 20 locomotives per month per manufacturer, components stockpiled for rapid assembly, assembly teams trained, maintenance manuals prepared in English and French, spare parts inventoried, the entire system designed for industrial-scale deployment. In June 1944, when Allied forces landed at Normandy, over 800 S160 locomotives were already in Britain, operating under temporary British Railway Company management. Another 400 were stored at Eby Junction in Wales, preserved and ready for shipment to the continent once ports could handle them. The Allies hadn't just planned to invade Europe, they'd planned to supply that invasion with an entire railway system built from American factories and shipped across an ocean. June-August 1944. The pattern of rapid advance followed by supply crisis repeated across France with predictable inevitability. The D-Day landings on June 6 succeeded beyond initial projections. Within 2 weeks, over 326,000 troops, 100,000 vehicles, and 500,000 tons of supplies had crossed the beaches. By the end of July, Operation Cobra broke through German defensive lines at St. Lo. The Americans poured through the breach. Patton's Third Army activated on August 1 and immediately began racing east and south. The liberation of Paris on August 25 symbolized Allied success but also exposed the emerging supply crisis. Paris lay 450 miles by road from the Normandy beaches, now the primary supply route since no major ports had been captured intact. Every ton of supplies required a 900-mile round trip for trucks. The Red Ball Express, hastily organized, threw 6,000 trucks into continuous operation. The system worked, barely. Truck convoys moved day and night along designated routes. Drivers worked 36-hour shifts. Maintenance was deferred. Accidents were common. By early September, the Express was losing 300 trucks daily to breakdowns, more than could be replaced. Fuel consumption was staggering. Delivering 1 gallon of gasoline to a tank required another gallon burned by the supply truck. First Army Commander General Courtney Hodges calculated that his units consumed 800,000 gallons of gasoline daily during active operations. Third Army under Patton burned similar quantities. The British Second Army and Canadian First Army added to the total. Ammunition expenditure peaked at 3,000 tons per day. Food, medical supplies, replacement equipment, spare parts, the list of necessities seemed endless. The mathematics were unforgiving. The 28 Allied divisions operating in August 1944 collectively required approximately 20,000 tons of supplies delivered daily to maintain offensive operations. The Red Ball Express delivered 12,000 to 13,000 tons on good days. The shortfall accumulated: 7,000 tons per day, 200,000 tons per month. Divisions began rationing ammunition. Tank units reduced operational sorties to conserve fuel. Artillery fire was restricted. By early September, Patton's Third Army had advanced 400 miles but sat immobilized near Metz, waiting for fuel. The First Army approached the German border but couldn't sustain combat operations. Montgomery's planned Operation Market Garden, the ambitious thrust to cross the Rhine, required supply priorities that starved other units of resources. The French railway system remained largely unusable. Allied bombing had done its job too well. Major bridges at the Seine, Loire, and Meuse rivers were destroyed. Marshalling yards at Rouen, Le Mans, and Reims were cratered. Most critically, virtually no functioning locomotives remained. The Germans had systematically removed or sabotaged their rolling stock during the retreat. The Allies controlled over 2,000 miles of usable track but could run almost no trains. Railway rehabilitation teams worked desperately. Combat engineers repaired bridges using Bailey bridge components, temporary structures rated for limited loads. Gangs cleared debris from marshalling yards. Track was inspected and repaired. But without locomotives, the reconstructed railways carried nothing. A few British locomotives were shipped across the Channel to test operations. The experiment failed. British engines, designed for the British loading gauge, couldn't pass through many French tunnels. Their wheel arrangements distributed weight differently than continental designs, stressing bridges and roadbeds. Parts were non-interchangeable with French railway standards. Captured German locomotives offered no solution. Over 100 different designs, many badly maintained, most sabotaged, all requiring specialized parts and trained mechanics familiar with specific models. The logistical nightmare of maintaining a fleet of non-standardized equipment was overwhelming. The Allies faced a choice: either slow the advance to match supply capacity or solve the supply problem before German forces could reorganize their defenses. Slowing the advance meant giving Germany time to establish new defensive lines, potentially extending the war into 1946 or beyond. Solving the supply problem meant deploying the railway system they'd prepared. In early September 1944, the first S160 locomotives began arriving at Cherbourg, the only major port then operational. 20 engines initially, then 50, then hundreds as port capacity expanded. Each engine required assembly, reattaching components removed for shipping, adding coal tenders, testing systems, training crews. But the standardized design meant assembly teams could process multiple engines simultaneously. By late September, the first supply trains pulled by S160 locomotives began operating on repaired French railways. The tonnage they carried, 1,500 to 2,000 tons per train, immediately dwarfed truck delivery capacity. One locomotive pulling one train moved what required hundreds of truck trips. The war's logistical crisis approached its turning point. The question wasn't whether trucks or trains would supply the Allied advance. The question was whether the railway system could be operational before the Wehrmacht reorganized its defenses. October 1944. The transformation of Allied logistics from truck-dependent to rail-enabled proceeded with industrial efficiency that surprised even optimistic planners. The S160 locomotives arrived in an accelerating stream. 50 engines in September, 120 in October. By November, over 300 were operating on liberated French railways. Each locomotive came with standardized documentation, operation manuals in English and French, maintenance schedules, spare parts lists, technical specifications. American Railway Operation Battalions, units specifically trained for military railway operations, provided initial crews and maintenance personnel. The advantages of standardization became immediately apparent. An S160 from Baldwin used identical components to an S160 from Lima or ALCO. Bearings, valve gear, boiler fittings, brake systems, complete interchangeability meant spare parts stocks served the entire fleet. A maintenance facility could service any engine regardless of manufacturer. Crews trained on one locomotive could operate any other. The comparison with German railway logistics was stark. The Wehrmacht relied on hundreds of different locomotive designs across occupied territories, each requiring specialized parts and trained mechanics. A breakdown in France might require parts from Germany transported across damaged networks installed by mechanics familiar with that specific design. The Germans' railway system was sophisticated but fragile. The American approach was crude but robust. S160 locomotives featured simplified maintenance requirements. Bearing inspection required basic tools. Boiler maintenance followed standard procedures. Coal and water were available throughout France. When an S160 developed problems, it could often continue operations with reduced efficiency until maintenance windows allowed proper repairs. The austerity design's simplicity became a strategic advantage. The capacity difference between rail and truck transportation revealed itself in operational data. A typical Red Ball Express 2.5-ton GMC truck carried approximately 5 tons of cargo per trip. The 2.5-ton designation referred to nominal capacity. Wartime overloading was standard. The 900-mile round trip from Normandy beaches to forward positions near Metz required approximately 54 hours, including loading, driving, and unloading. Each truck consumed roughly 100 gallons of gasoline for the round trip. An S160 locomotive pulling a 50-car freight train hauled 1,500 to 2,000 tons, the equivalent of 300 to 400 truckloads. The trip from coastal ports to forward railheads took 12 to 16 hours, depending on route conditions. Coal consumption was approximately 15 to 20 tons per trip, locally sourced, not imported from the United States. One locomotive could complete one trip daily, delivering as much as hundreds of trucks. The mathematics favored railways overwhelmingly. By November 1944, approximately 150 S160 locomotives were in regular operation moving military freight. If each completed one supply run daily, they delivered 225,000 to 300,000 tons per day, roughly 20 times the Red Ball Express maximum achieved in August. The actual figures were lower due to infrastructure limitations, maintenance schedules, and traffic control challenges. But even at 50% efficiency, the railway system transported more tonnage than the entire truck fleet. Most importantly, railway operations freed truck convoys for shorter hauls, port to railhead, railhead to forward positions, where trucks' mobility advantages were decisive. The transition from truck-dependent to rail-enabled logistics became visible in operational results. In September, Patton's Third Army had been immobilized near Metz for lack of fuel. In October, with rail supply lines operational, Third Army resumed offensive operations. In November, First Army pushed toward the Siegfried Line with adequate ammunition stocks. The chronic supply shortages that characterized August and September disappeared. But the railway system faced continuous challenges. German artillery occasionally shelled rail lines near the front. Sabotage by collaborators damaged tracks and signals. The rapid Allied advance meant railway rehabilitation teams constantly worked to repair and extend lines forward. Bridge capacity limited train weights. Temporary Bailey bridges carried lighter loads than destroyed permanent structures they replaced. The S160's design proved well-suited to these challenges. The locomotive's weight distribution, 8 driving wheels spreading approximately 160,000 pounds, allowed them to cross temporary bridges rated only for lighter loads. Their simplified controls enabled relatively inexperienced crews to operate them with short training periods. French railway workers, pressed into service by Allied military government, learned S160 operation within days. The nickname "Spam Cans on Wheels" gained circulation among American troops, referencing the locomotive's utilitarian appearance and mass-produced nature, but the nickname carried grudging respect. These crude engines worked. They hauled the supplies that kept offensives moving. They burned coal that didn't compete with gasoline needed for tanks and trucks. They operated in conditions that would sideline more sophisticated locomotives. The contrast with pre-war American railway practice was profound. American railroads in 1940 operated some of the world's most advanced locomotives, streamlined, powerful, refined machines designed for decades of service. The S160 represented the opposite philosophy: adequate performance, minimal refinement, designed for wartime utility and post-war disposal. Major Marsh, the S160's designer, had achieved exactly what military specifications required: a locomotive that could be mass-produced, shipped across an ocean, operated by minimally trained crews, maintained with basic tools, and delivered sufficient performance to sustain military operations. The design sacrificed everything unnecessary to that mission. No copper domes, no ornamental brass, no refined valve arrangements, just functional machinery built to win a war. By December 1944, over 400 S160 locomotives were operating across France, Belgium, and Luxembourg. The railway system was moving approximately 200,000 tons of military freight daily, more than the entire Red Ball Express ever achieved. Truck convoys still operated, but in supporting roles, moving cargo from railheads to forward positions rather than making the full journey from ports. The logistical crisis that threatened to stall the Allied advance had been solved not through tactical brilliance or operational innovation, but through industrial capacity applied to an ancient technology. Steam locomotives, 19th-century technology, had proven more decisive than any 20th-century weapon system. The Wehrmacht recognized this. German intelligence reports from November 1944 noted with alarm the American ability to sustain operations at extended distances. They had expected supply limitations to force operational pauses, creating opportunities for counterattacks. Those pauses never came. The Americans just kept advancing, supported by an apparently inexhaustible supply stream. What German intelligence didn't fully comprehend was that the supply stream depended not on sophisticated logistics, but on crude locomotives built to be disposable. The S-160s weren't secret weapons. They were visible to anyone near railway lines. But their strategic impact, enabling sustained offensives at distances that should have been logistically impossible, surprised German planners who had assumed the Allies faced the same railway limitations Germany did. The assumption was false. The Germans were trying to operate captured locomotives across non-standardized networks. The Americans had brought their own railway system with them, built in Pennsylvania and shipped across an ocean. The advance continued. The crisis had passed. The humble S-160, crude and unlovely, had become the logistical backbone of the final campaign against Germany. The S-160's design reflected a fundamentally different approach to locomotive engineering than any peacetime railway would accept. Traditional locomotive design prioritized longevity, reliability, and performance across decades of service. American railroads in 1940 operated engines built in 1900, still earning revenue. Design specifications emphasized durability, forged steel frames, riveted boilers, refined bearings, quality materials throughout. The expectation was 40 to 50 years of service, hundreds of thousands of miles traveled, millions of tons hauled. Capital cost was amortized across decades. The S-160 rejected this philosophy entirely. The design assumption was 5 to 10 years maximum service life, probably less. Why build for 40 years when the war might end in 2 years and the engines would become surplus? Why use forged steel when cast steel was faster to produce and adequate for limited service life? Why rivet boilers when welding was faster and sufficient for wartime duty? The specific design choices demonstrated this philosophy in detail. Frame construction. Cast steel frames instead of forged. Cast frames could be produced in weeks using molds. Forged frames required months of heating, hammering, and forming. The cast frame was heavier and less elegant, but perfectly adequate for an engine designed to operate 5 to 10 years. Boiler design. Welded construction instead of riveted. Welding was faster and required less skilled labor than riveting, critical when locomotive shops were already overwhelmed with orders. The welded boiler wouldn't last as long, but would serve adequately for wartime requirements. Running gear. Simplified bearing arrangements using standard components. Pre-war locomotives featured refined bearing systems requiring precise machining and careful maintenance. The S-160s used simpler designs with loose tolerances, noisier, requiring more frequent inspection, but easier to manufacture and service with basic tools. Valve gear. Walschaerts valve gear, a proven design requiring minimal adjustment. More sophisticated valve systems offered better performance but demanded skilled mechanics for maintenance. The S-160's valve gear was straightforward enough that relatively inexperienced crews could maintain it. Cab design. Spartan shelter with minimal weather protection. Pre-war locomotives featured enclosed cabs with creature comforts for crews. The S-160's cab was barely adequate, sufficient for wartime duty but uncomfortable. This saved weight, manufacturing time, and materials. Finishing, minimal. No copper domes, no ornamental brass, no polished surfaces. The locomotives were painted flat gray or black, given identification numbers, and shipped. Peacetime locomotives were works of industrial art. S160s were industrial tools. The philosophy extended to maintenance procedures. Traditional locomotives required skilled mechanics familiar with specific designs. The S160 was designed for semi-skilled maintenance, standard tools, simple procedures, interchangeable parts. American railway operation battalions trained mechanics in weeks rather than months. The design also anticipated field modifications. Different theaters had different requirements: steeper grades, tighter curves, different fuel qualities. The S160's simple design allowed modifications without extensive engineering. In Italy, crews modified some engines for heavier service on mountain grades. In France, some received altered coal bunkers for local coal types. The standardized design made such modifications straightforward. But the crucial philosophical difference was the acceptance of limitations. Pre-war locomotives were designed to handle whatever service conditions arose over decades. The S160 was designed specifically for European operations in 1944-1945. It fit European loading gauges, it burned European coal, it performed adequately on European grades and curves. It didn't need to be excellent, it needed to be sufficient. This sufficient philosophy extended to production planning. The Army ordered 2,120 locomotives, knowing many would never enter service, become surplus, or serve only briefly before the war ended. This was acceptable. Overproduction was cheaper than underproduction. Surplus locomotives could be sold to European railways after the war. The cost of building too many was far less than the cost of building too few. The comparison with German railway logistics highlighted the American advantage. Germany operated sophisticated locomotives designed to exemplary engineering standards, but those standards created vulnerabilities. Precision manufacturing required intact factories, specialized parts required intact supply chains, skilled mechanics required years of training. When Allied bombing damaged factories and supply chains, German railway efficiency collapsed. The Americans built locomotives that didn't require precision manufacturing, that used standardized parts available for many of 3 manufacturers, that could be maintained by semi-skilled mechanics trained in weeks. The sacrifice of engineering elegance bought strategic resilience. The S160 also reflected American industrial capacity advantages. Germany couldn't have built 2,000 locomotives between 1942 and 1945 while also producing tanks, aircraft, U-boats, and all other war materiel. American factories built 2,000 S160s while simultaneously producing thousands of aircraft, hundreds of ships, tens of thousands of tanks, millions of trucks, and essentially unlimited ammunition. The crude design enabled this industrial achievement. Complex locomotives require skilled labor and specialized facilities. Simple locomotives can be built on production lines using semi-skilled workers and standard manufacturing equipment. Baldwin, ALCO, and Lima all adapted their facilities for high-volume S160 production while maintaining capacity for other projects. Post-war analysis by railway engineers noted with interest that the S160, despite its austerity design, performed reliably in service. The expected 5 to 10-year service life was exceeded. Many S160s operated into the 1960s in European service, some into the 1980s. The disposable locomotive proved more durable than designed. But this wasn't the design intent. The intent was sufficient performance for wartime requirements at maximum production speed and minimum manufacturing complexity. That the locomotives lasted longer than expected was a bonus. The war wasn't won by locomotives designed to last 40 years. It was won by locomotives designed to be built quickly and work adequately. The S160 represented industrial pragmatism at its most ruthless. Build what's needed, when it's needed, as fast as possible. Accept limitations, plan for surplus, prioritize production over perfection. It was the philosophy of a nation with overwhelming industrial capacity applied to a logistics problem that could only be solved by overwhelming that problem with sheer productive output. The elegance was in the philosophy, not the product. December 1944 to March 1945, the S160 locomotives proved their strategic value during the war's final winter when sustained operations across damaged infrastructure determined outcomes. The Battle of the Bulge in December 1944 demonstrated both the vulnerability and resilience of Allied logistics. When German forces broke through American lines in the Ardennes on December 16, they captured forward supply dumps and disrupted truck convoys. The offensive specifically targeted Allied supply lines, attempting to recreate the logistical strangulation that had threatened the advance in August-September. But the railway system, now firmly established, provided resupply capacity the Germans couldn't interdict. S160 locomotives operating from major railheads at Liège, Verdun, and Luxembourg delivered continuous flows of ammunition, fuel, and reinforcements. The Germans captured some forward truck depots but couldn't reach the major railway infrastructure protected behind Allied lines. The mathematics of railway supply proved decisive. First Army's counterattack required moving 250,000 troops and 50,000 vehicles into the Ardennes salient. Truck convoys moved troops rapidly but consumed fuel doing so. Railways moved heavier loads, ammunition, fuel, heavy equipment, freeing trucks for tactical movements. Third Army's famous 90-degree pivot from Lorraine to the Ardennes required moving vast ammunition stocks to new positions. Railway freight handled most of the tonnage. By January 1945, over 500 S160 locomotives were operating across France, Belgium, Luxembourg, and newly liberated portions of the Netherlands and Germany. The railway system had expanded to include main supply routes from channel ports, Cherbourg, Le Havre, Antwerp, to forward railheads, secondary lines serving individual armies and corps, specialized ammunition trains with armored cars for forward delivery, hospital trains evacuating wounded to rear area medical facilities, maintenance trains carrying railway repair equipment and crews. The organizational complexity matched the physical infrastructure. American railway operation battalions managed operations, coordinated schedules, maintained equipment, and trained additional personnel. French railway workers provided local knowledge and labor. British railway engineers assisted with technical challenges. The system functioned as a multinational logistical network united by standardized American locomotives. The S160's rugged simplicity proved advantageous in winter conditions. Sophisticated locomotives struggled in severe cold, frozen water lines, brittle lubricants, temperamental controls. The S160's crude systems worked regardless. Steam heat prevented freezing. Simple bearings tolerated cold lubricants. Basic controls remained functional. The locomotives were uncomfortable for crews in winter weather, but they operated. Maintenance statistics revealed the design's effectiveness. A typical S160 required major maintenance every 15,000 to 20,000 miles of operation, approximately 6 to 8 weeks of continuous service. Compare this to more sophisticated locomotives requiring maintenance every 10,000 to 12,000 miles. The longer service intervals meant more locomotives in operation at any time, fewer tied up in maintenance facilities. The standardization advantage became even more apparent as the fleet grew. Spare parts inventoried for 500 locomotives served all 500 identically. Maintenance facilities trained mechanics on standard procedures applicable to every engine. Operational manuals were identical across the fleet. This standardization would seem obvious today, but was revolutionary in 1944 when most railways operated multiple incompatible locomotive types. By February 1945, as Allied forces prepared for the Rhine crossings, the railway system was moving an estimated 300,000 to 350,000 tons of military freight daily, far exceeding the tonnage Red Ball Express ever achieved. This capacity enabled the massive supply buildups necessary for the final offensives into Germany. The Rhine crossing operations in March 1945 demonstrated logistics at industrial scale. Operation Plunder, Montgomery's crossing at Wesel-Rees on March 23-24, involved 1.2 million troops supported by railway networks delivering ammunition for 4,000 artillery pieces that fired 4 hours of continuous bombardment. The logistics of merely delivering artillery ammunition for that bombardment would have been impossible without railways. Patton's opportunistic crossing at Remagen, though smaller, still required rapid buildup of supplies to exploit the captured bridge. Railways delivered the bulk tonnage, pontoon bridge components, engineering equipment, ammunition stocks, while trucks moved assault forces and tactical supplies. The division of labor between strategic railway transport and tactical truck movements had become standard practice. As Allied armies pushed into Germany in April 1945, S160 locomotives followed close behind advancing forces. Railway rehabilitation teams repaired damaged German railways, often using captured German materials but American locomotives. The S160's design, built for European loading gauges, meant they could operate on German railways immediately, no modifications needed. The final statistics for S160 operations in Europe are incomplete. Military records focused on tonnage delivered, not specific locomotives hauling it, but approximate figures demonstrate impact. Over 600 S160 locomotives in European theater by war's end, estimated 15,000 to 20,000 trips completed by fleet through May 1945. Approximate total tonnage, 30 to 40 million tons delivered via rail. Precise figure impossible to determine, includes all locomotives, but S160s constituted majority. Railway tonnage far exceeded truck delivery even during maximum red ball operations. The human cost was surprisingly low. Unlike combat units, railway operations occurred behind lines in relatively secure areas. Accidents caused most casualties: derailments, boiler failures, coal handling injuries. German air attack rarely targeted railways after 1944 due to Allied air superiority. Artillery rarely reached railway infrastructure except near front lines. The S-160 crews, American military railway personnel, and French railway workers developed mutual respect despite language barriers and different operating traditions. American crews appreciated French railway workers' expertise with European rail systems. French workers appreciated American locomotives' power and reliability compared to war-damaged French engines. One French locomotive engineer, interviewed after the war, commented, "The American locomotives were ugly, crude machines, but they worked. Every day, every night, rain or snow, they worked. We hauled ammunition that killed Germans, we hauled food that fed French civilians, we hauled everything an army needs. The locomotives were not beautiful, but they were beautiful to us." This pragmatic appreciation captured the essence of the S-160, not a triumph of engineering elegance, but a triumph of industrial pragmatism, built to be sufficient, not excellent, designed to be produced quickly, not last forever, intended to solve an immediate problem, not represent technological advancement. By May 1945, when Germany surrendered, the S-160 fleet had become so embedded in European railway operations that immediate withdrawal was impossible. The locomotives continued operating through summer 1945, hauling displaced persons, reconstruction materials, and occupation supplies. Their wartime mission had ended, but their utility continued. The S-160 production and deployment statistics tell the story of American industrial capacity applied to military logistics. Total production, 2,120 locomotives built between 1942 and 1945. Manufacturers and approximate output: Baldwin Locomotive Works, approximately 800 units. American Locomotive Company, ALCO, approximately 800 units. Lima Locomotive Works, approximately 520 units. Production rate: peak monthly output reached approximately 60 to 70 locomotives across all three manufacturers combined, 1943 to 1944. Specifications, as built, wheel arrangement, 2-8-0, consolation type. Weight, locomotive only, approximately 160,000 pounds or 72 tons. Weight with tender, approximately 250,000 pounds or 112 tons. Driving wheels, 57 inches diameter. Cylinders, 19 inches bore times 26 inches stroke. Boiler pressure, 225 psi superheated. Tractive effort, 31,490 pounds. Maximum speed, approximately 50 miles per hour, rarely achieved in wartime service. Coal capacity, tender, 8 tons. Water capacity, tender, 5,400 gallons. Geographic distribution, approximate 1945. Great Britain, 400 units, operated by British Railways during build-up, most later transferred to the continent. France, 300-plus units. Belgium, Luxembourg, 100-plus units. Netherlands, 50-plus units. Italy, 250-plus units. Germany, captured railways, 150-plus units. North Africa, Middle East, 200-plus units. Other theaters, the remainder. Post-war disposal. The Army sold surplus S160s to numerous countries rather than ship them home. Post-war distribution included Poland, 575 units, became PKP classes TR-201/TR-203. Soviet Union, 200 units, became class SHA, including broad-gauge conversions. France retained many wartime units, became SNCF 230G class. Italy, 243 units, became FS Class 736. Greece, Yugoslavia, Hungary, Austria, and other European nations purchased smaller numbers. Many S-160s operated into the 1960s to 1970s in European service. Some survived until the 1980s. Approximately 26 units survive today in preservation, scattered across Europe and the United States. Comparative analysis: an S-160 hauling a 50-car freight moved approximately 1,500 to 2,000 tons per trip. This equaled 300 to 400 truckloads, 2.5-ton GMC trucks, the cargo capacity of a small cargo ship, more tonnage than the entire daily output of some Red Ball Express convoy routes. Cost comparison is difficult due to wartime accounting, but approximate figures suggest one S-160 locomotive $150,000 to $200,000 $1944, one GMC 2.5-ton truck $2,500 to $3,000 $1944. One S-160 equaled 60 to 80 trucks in cost, but moved hundreds of times more cargo over its service life. The efficiency difference becomes stark in operational economics. Fuel: S-160 burned coal, locally sourced in Europe, versus trucks burned gasoline, imported from the United States. Personnel: one S-160 required 2 to 3 crew members versus trucks required hundreds of drivers to move equivalent cargo. Maintenance: standardized parts and procedures versus diverse truck fleet requiring multiple parts supply chains. The philosophical difference: the S-160 represented industrial pragmatism, adequate performance, maximum production speed, accept limitations, plan for surplus. Compared to German railway approach: excellent performance, traditional manufacturing, minimize redundancy, optimize for peacetime efficiency. The American philosophy won because war rewards quantity and reliability over quality and sophistication. A fleet of crude locomotives that worked continuously defeated smaller numbers of sophisticated locomotives that required specialized maintenance. May 8, 1945, victory in Europe. Across the shattered continent, S-160 locomotives continued operating as they had every day since deployment, hauling freight, burning coal, moving the endless tonnage that modern armies consume. There were no ceremonies for these locomotives, no medals for their crews, no newsreel cameras filming their operations. The public memory of World War II logistics focused on heroic images: the Red Ball Express trucks racing through French countryside, brave drivers delivering supplies under fire, the American can-do spirit overcoming Nazi tyranny. The reality was less photogenic but more decisive. The war was won by crude steam locomotives built to be thrown away, operating on damaged railways, hauling ammunition and fuel that nobody saw until it exploded or burned. The S160s were the logistical backbone of victory, but backbones don't generate headlines. The irony runs deep. In 1944, military planners worried whether these crude engines would perform adequately for even short-term wartime service. In fact, many S160s operated for 30 to 40 years after the war ended. The disposable locomotive outlasted the conflict it was designed for by decades. European railways, devastated by war and lacking capital for new equipment, gratefully accepted surplus American engines that worked reliably despite their austerity design. The S160's post-war career validated a principle that peacetime engineers had rejected: adequate and available beats excellent and delayed. A perfect locomotive delivered in 1950 helps nobody in 1944. A crude locomotive delivered in 1943 might win a war. This lesson extends beyond locomotives. Modern military logistics still grapples with the tension between optimal designs requiring years of development versus adequate designs available immediately. The S160 precedent argues for adequate and immediate. The counterargument notes that crude solutions aren't always sufficient. Sometimes excellence is required. But World War II logistics suggests excellent is often the enemy of sufficient. The Wehrmacht operated excellent railways using sophisticated locomotives and complex logistics. The system worked magnificently when infrastructure remained intact, but collapsed when Allied bombing damaged that infrastructure. The Americans operated adequate railways using crude locomotives and simple logistics. The system worked regardless of conditions. The strategic lesson is uncomfortable for engineers. Crude solutions that work reliably often defeat sophisticated solutions that work optimally. Reliability trumps capability. Simplicity trumps refinement. Available trumps optimal. The S160 embodied this lesson. It was never the best locomotive built in 1943. It was probably among the crudest, but it was available in sufficient numbers when needed, operated reliably in harsh conditions, required minimal maintenance and training, and could be produced at industrial scale. These attributes, not technical excellence, won the European campaign. The locomotive's fate mirrors its philosophy. Most were scrapped eventually, serving their purpose and then disappearing. A few survive in museums, curiosities from a war when industrial capacity could be weaponized, when crude machinery shaped strategic outcomes, when good enough was better than excellent. The S160 wasn't the reason the Allies won in Europe, but it was a perfect symbol of how they won: overwhelming problems with industrial capacity, accepting crude solutions that worked, prioritizing availability over optimality, and proving that in total war, logistics trump tactics and quantity trumps quality. The crude machines built to be thrown away helped win the war. Some are still running.